Hello, good morning. Can you hear me?
Yes, good morning.
Hello, this morning we shall discuss how to implement ecological models uh, starting from very different perspectives in terms of scales. For example, we have already seen last week Moni's model, but is modeling nutrient emission into river system, but is a model but it is based on GIS techniques in order to model at a landscape scale the process of nutrient generation that brings nutrient loads into river system. Later we will see another model on deposit scale, a model on the scale of a population or on the scale of the organisms or on the scale of a single organisms processes. Concerning landscape models, we have said that we shall employ GIS tools, geographical information systems, that allows us to gather a lot of information, but it's georeferenced information. And this information may be collected into layers that implement a description of a portion of land that is specific of the task the model is designed for. We said that in order to build these models, we collect information into layers, geographical layers, and then we combine these layers in order to produce geographical maps of the outputs of a landscape model. I recall you that a GIS system consists of hardware, software, data, staff, and training. We have said this, we have discussed all these topics, and I suppose you already know these things because you have already followed the GIS class during your study course. I recall you that GIS maps or geographical layers may be of three general types: points, in which the element of the layer represents single points on space, three-dimensional space; vectors, in which instead of points we have lines, but a vector is a point, a starting point, and a direction and the length; and then maps, in which we subdivide the territory cells, and each cells it is attributed different characteristics or attributes describing the particularities of this portion of space. We said also that points and vectors are scale independent descriptions, meaning that we employ geographical coordinates for defining points and vectors, while when we employ maps description, we have raster maps. This means that we have to define a priori a scale, and the smallest element of a scale is the cell of a raster map. We have said that by employing GIS software, we have implemented a model of nutrient emission on a landscape scale or a catchment river system. So here we are modeling a very large ecosystem. Large meaning that we are talking about kilometers in space and months or years in time scales. We said that the unit in the Moneris model is the catchment or sub-catchment, and we have said that once we may implement this description, we shall end up with a steady state model in which we have a distributed approach systems. This means that we change the parameters depending on the position, the space position, and depending on the time. The spatial scale, as we said, is the hydrological unit or sub-basin, but is larger than 50 square kilometers, so very large units, while the temporal scale is annual or pluriannual. The scope of this model on a landscape scale is that of evaluating nutrient emissions from complex river systems in order to evaluate how much is the impact of anthropic activities on a particular portion of land. We said that the model structure is built up based on an input data spreadsheet in which we include general information, information concerning flows and loads, so discharges and loads, information concerning municipalities, meaning number of inhabitants and surface of arable land, and information concerning land use, the soil type, or pedology in Italian, geology, that is what we are expecting to find immediately beneath the surface of land. Then we include some chorographical information like the slope, and some atmospheric information like precipitation, atmospheric deposition, and so on. In order to evaluate the anthropogenic impact, we have also to include information concerning human activities, like, for example, agriculture. And for this, we include a layer describing agricultural surplus. And we also have to include information concerning urban systems, in particular, the presence of wastewater treatment plants and the extension of separate or combined sewer system. Moneris is an example of a complex model in which we include a large set of pathways. These are the pathways considered by the model we are applying here. So atmospheric deposition, agricultural surplus, soil erosion, groundwater, overland flow point sources, urban systems, and the background. We combine all these layers with pathways in order to have an estimation of the loads generated by a portion of land on the receiving water system, water body. The model structure is depicted in this slide. So we have input data, but essentially are catchment description. And these input data are employed to vehiculate loads through the different pathways. And then we collect all the information on the final spreadsheet file called Moneris, in which we have a summary of what is happening on the territory. I stress again that the model this model tries to include a lot of details on a complex ecological system, that is, for example, a river catchment and the effects of this river catchment onto the surface water qualities, onto groundwater quality, and finally onto the water quality in the coastal zones in terms of loads, nutrient loads discharged by the river system to a coastal zone. We said that we have to include also a retention model in order to describe the fact that water system have a self-purification capacity due to the fact that some biochemical processes, like, for example, nitrification, denitrification, or volatilization, and so on, may happen so that the loads generated by portion of land are reduced by this model. The model, this is a experimental model in which we collect a series of experimental data concerning European catchments, and we try to define the two parameters of this retention model, A and B, that describe the effect of water passing through this ecosystem in terms of retention times. So a model describes the ratio between loads, so what is arriving onto a water body, and emission, what is generated onto a surface, on the surface of a catchment by um, human activities, anthropic activities, and so on. Sorry. Okay, so what we are doing here, we are trying to model a very complex system in which several actors may have a significant role with a mathematical model the most simplified as possible, because as we have said several times, we are seeking for the highest complexity but with lowest um, computational demand. So we want a manageable model in terms of computational demand and in terms of availability of data. As you see, and you can imagine, when you deal with such large ecosystem, with such heterogeneous processes, you of course have to give up the pretension to know all the details of the system. So we are in a holistic approach in which we look at the generality of the globality of the system, and we try to describe globally the behavior of the system without going too much details. We showed the application to this model of a poor catchment area. The poor catchment area, but the Po River is one of the largest river in Europe. This is a depiction of a catchment area. You see the Alps here and the Apennines here, but contributes to the Po River main course in terms of nutrient load. So this area is strongly anthropogenically impacted. I recall you that the surface is very large, so we are talking here about 1,073,000 square kilometers, and we are talking of the effect of a population of millions of inhabitants, 70 millions of inhabitants in this case. Said that this area has an important relevance in terms of economic impact on the GDP. 40% of the GDP come from this area. In Italy, 46% of employment, 37% of industrial production, 35% of agriculture, 55% of cattle raising is performed on this area. The agricultural activity produces impact on 3.4 million hectares. This is 45% of agricultural arable land. And here we grow wheat, maize, fodder, barley, sugar, and so on, all this staple food. And we grow also more than 1 million of hectares are employed as permanent meadows and pastures for cattle and pigs. So this is a very important economical and agricultural area. We said also that the Po River is a hydrological monster in terms of discharge. The average discharge of a river calculated on the last 60 years is around 1,500 cubic meter per second. So this is a very large discharge, but it is a testimony of the fact that we are dealing with a very large ecosystem, very complex ecosystem. And we have said that the management authorities of the Po River Basin have estimated in the past 10,000 tons per year of nitrogen loads, 9,000 tons per year of phosphorus loads. Of these loads, 63% comes for nitrogen comes from diffuse sources, while 42% for phosphorus comes from diffuse sources. And then we said that we gather all this information concerning the subbasin. So the subbasin of the model, or the hydrological subunits, are 33. In this case, for each one of these 33 subbasin, we need to find good station for which we need to have information on discharge and information of the surface that is contributing to the catchments in terms of discharge. Uh, uh, okay, we collected a lot of information concerning population in terms, for example, of statistics of municipalities. We employed the ISTAT subunits, that is the Italian Statistical Agency, that collects for each of these subunits what are more than 6,000 information concerning the number of inhabitants and the surface of total arable land. We include information concerning land use, which is geographical information collected from satellite imageries. We include information on the geology, what we are expecting to find of subsoil, information of the digital elevation model, that means slopes, essentially, and elevations, and then information concerning meteorology, for example, precipitation, and also transpiration as well. Precipitation and evapotranspiration. You see that the data that we are collecting of very different sources and very different scales. And the idea is that we try to collect all this information, for example, by employing software tools like the GIS modeling system, in which all this information may be collected and assembled into map layers. By this, we also include information on nutrient surplus, which is the consequence of agricultural activities. So in terms of nutrient surplus, in terms of nitrogen and phosphorus, and this is calculated as the difference between fertilizer plus manure employed by agricultural activities minus nutrients what are taken away by yield, so what it is put on the market. We had to include also the effect of the urban system, so information concerning wastewater treatment plants that are discharging loads of phosphorus and nitrogen in the area. Then we put all this information together and we obtain by the hydrological balance or water balance, we obtain a first estimation of a quantity of water that may be expected to be found in the various closure points of 33 sub-basins or the 33 sub-hydrological units. Please note that we are not modeling in detail water flow generation. Instead, what we are doing is that we are employing our knowledge concerning the discharges measured at the different closure points of the sub-basins. We act on the model in order to change the behavior of the model, so that at least we force into the model our knowledge concerning the hydraulic balance, so that what we force all the points of the 33 points of the sub catchments outcomes or outlets on the one-to-one line, so that what we are doing here is that we are forcing the model to produce the water discharge as we measured it on the territory. So we are putting on the side all the details concerning the hydrological balance. Instead, we are employing our knowledge, but it comes from observation, experimental observation, what's happening to along the river, so that we force and we hinder all the complexities linked to a hydrological balance into the background by simply forcing the behavior of the model and producing exactly the discharge that we are measuring, so that we are left with the problem of nutrient production and vehiculated through the different pathways. And so this is what the model produces along the main river pathway. So these are the distances from the springs, 100, 200, 300 kilometers distances from the spring down to the outlet of the river, that is 600 kilometers length, more or less, 570. So we have in blue measured values of nitrogen loads, in pink measured values of nitrogen calculated, nitrogen loads calculated by the model, and the same for phosphorus. So we compare phosphorus as measured or gathered information from experimental processes, experimental procedures, observations, and the, the load produced, phosphorus or nitrogen loads produced by calculated by the model itself. By this subdivision, we may immediately stress which are the most relevant pathways for the two different nutrients. For example, we discover that for groundwater is mostly impacted by nitrogen emissions. This is, of course, leaching, water leaching from the surface and bringing nutrients from the agricultural activities or from on the other side, we have also an impact that is significant in terms of wastewater treatment plant or in terms of urban ecosystems for nitrogen in particular, while for phosphorus it is irrelevant, but the overland flow that brings solid transport with it, and tile drainage or wastewater treatment plants are the most important pathways in terms of production of loads of phosphorus. So we, after this analysis, we may generate geographical maps of a catchment in which we may individuate or we may stress which are the most significant subcatchments in terms of production of the two different types of loads, the nitrogen and phosphorus. So you see, by this application, we may identify some places along the main river courses, the reddish one, in which the impact is most significant. So these are what we may call critical spots. This kind of application is very helpful in order to evaluate different management scenarios by which, for example, we may change some of the value on the input data and observe what happens in terms of nutrient produced or nutrient load production into a catchment. So this is an example of a very large model, a model of a very large ecosystem in which there are several complex processes taking place and for which we try to collect all the large amount of information in several ways, trying to make it the most homogeneous as possible on a very large scale. On the contrary, now we switch to a completely different scale so that we look now at how, sorry, where we are now. Uh-oh. Okay. We now change completely our reference scale and instead we try to build up a model describing what happens into single organisms. So you see we are looking, we are completely changing, we are on the other extreme of the resolution of spatial resolution applicable. In this case, we concentrate, we focus on a single organisms. For example, we look at fishes, an important indicators of water ecosystem. By doing what we try to build a fish growth model. That is a model that it is able to describe what happens to higher trophic level. In particular, we know that fish feeds on algae and or zooplankton. So what we are doing here, we are trying to model higher trophic levels instead of a primary production. You may recall that we said that the lowest trophic level is that of a primary production or algal growth. The next lecture will be all devoted to developing algal growth model. It is the base of all the trophic chain or the trophic pyramid. And for which we shall start our analysis by looking at the physiology of these animals. In particular, let us concentrate on fishes that are simple, quite simple animals. And for these animals, we recognize that growth depends on species-specific characteristics, and some environmental factors. These are the age, but is a species-specific, environmental temperature, but is an environmental characteristic, the ration of food ingested, but is in between species-specific and environmental characteristics, meaning if there is enough food for the animal depends on the environmental characteristics, and then of the body size, but is a typically species-specific characteristic. So you see, we are completely changing. We were modeling catchment, 70,000 square kilometers. Now we are modeling small animals, so centimeters or seconds or maybe days or seasons. Historically, the first models that were employed to describe fish growth were empirical models. We may recall the logistic growth model. We have already cited here in bed. The only true model that is applicable to limited growing systems. Then there are some variation of the logistic, the Gompertz model, the von Bertalanffy model, that is a generalization of the logistics, and the Richards model. All these applications are based on a best fit of the parameters, but do not have a precise meaning. But instead, what we try to do is we try to uh, change the behavior of the model so that the output of the model produces a kind of sigmoidal behavior, which, for example, we link population and time, and we have a limiting effect that is depicted by the carrying capacity. The logistic growth model or logistic growth curve is a sigmoidal curve, but there's an inflection point in the middle. Sorry, one moment. Okay, we said the sigmoidal curve, it is the prototypical representation of a limited growth model, which we try to describe by metabolic consideration how these first low trophic levels may be described. In particular, the sigmoidal curve is a curve that displays an inflection point. The inflection point is the point at which there is a changing in the concavity, and you may recall that in this point, the second order derivative is maximal. So the point of inflection, the point in which you have a changement of concavity, is the point of maximum growth rate or growth speed for the population. So you see, we are changing completely here from our perspective, from looking at catchment, and we instead we put our focus into the physiology of the animal. In order to build a metabolic growth model, we have to consider that there are several factors affecting growth. What we may subdivide into two categories: intrinsic and extrinsic factors. Intrinsic factors are the species-specific, race, dimensions, or species-specific like swimming activities and maturities and so on, while the extrinsic factor depends on the conditions of environment. And based on their term may be subdivided into abiotic or biotic factors. For the abiotic factors, we may consider the photoperiod, for example, presence of light. You may recall that we are talking about the second trophic level, so the trophic level that fits directly on primary production, and you may recall that primary production depends dramatically by the presence of sunlight, so the photoperiod is an important characteristic for describing primary production. Of course, temperature, as we will see in the following lectures, is an important parameter. The presence of oxygen, you may recall that presence of oxygen is a proxy of photosynthetic activity. pH, CO2 are all parameters that are all characteristics that influence the primary production activities. the presence of toxic substances, but also the salinity levels. The biotic factors on the other way are, for example, the diet, so what they eat, the rations, how much they have available for feeding, the feeding frequency, the presence of parental care that changes dramatically the behavior of the first period of life of the offsprings, or the presence of disease, or the presence of social factors like, for example, social hierarchy. In order to build uh, this model of metabolic growth analysis, we start as a customary from the, as we have always done from um, energy conservation principles. So we employ a continuity equation again. This time we try to describe the fate of a consumed food. We may use units of mass or energy, and we may start saying that the consumed food goes partially is lost into feces. What is not lost, it is assimilated material. Of the assimilated material, some of the energy is employed for specific dynamic action, uh, or some of this energy is employed for the activity of digestion. So we have to subtract these two quota of the energy from the assimilated material. Some is lost through the urines or excretion from gills and skins. Of what it rests with is metabolism about material, or materials that may be employed, that may be metabolized by the animal. Of these we have, we may subdivide it again to three quarters. The first one, that is the other activities like swimming, hunting, and so on, RA. The third one is the basal metabolism, what we call RS, that is the energy employed by starving organisms. So the energy employed as a base energy for keeping the animal living. What it remains of all after all this composition is what it may be transformed into new biomass of this organism, what we may call growth. I will indicate with B. What is B? By simply employing the mass conservation, we may say that B, the biomass, the growth, is equal to the consumed food minus various factors, uh, losses in feces, losses in urine, and losses due to the energy consumption due to the biology and physiology of the animal. These losses are made up of losses due to basal metabolism and losses due to specific dynamic actions and losses due for other activities like swimming or hunting or building nests and so on. So you see, we are trying to, by conceptualization of this model, to subdivide the different processes that have effect on the growth process of second trophic level organisms, so the organisms that feed on the primary production. And by doing this, we obtain a model in which we write that the variation times of the weight of the animal, so maybe fish mode, is a general model that is based on the assumption that the metabolism is maybe subdivided into two terms, anabolism and catabolism. Catabolism is the quota of energy that is necessary to maintaining alive the organisms, while anabolism is the quantity of material that is, or the quantity of energy that is directly converted into new biomass of this organism. So we may, if we introduce W as the fish weight, we may write in terms of a differential equation, first order differential equation, but the variation in time of a weight of a fish is equal what goes in minus what goes out. You know very well this approach. We use the approach of the continuity equation, but it's the translation of the energy conservation principle. W, so the weight of the fish may be expressed in dry weight, so we indicate d dot W dot, meaning dry weight, or wet weight, meaning we may indicate it by W dot W dot, meaning that we are weighting the organism, the biomass of the organism without drying it, so including the water. So the assumption, the basic assumption for the building this metabolic growth model is that ingested food and the biomass of the fish itself have approximately the same chemical composition. This is not such a strong approximation or not such a strong assumption because you know that the fixed stoichiometry principle for organic matter tells us that all organic matter have more or less the same composition if you subdivide it in terms of lipid, carbohydrates, or proteins, or if you subdivide it in terms of, for example, different types of biomasses, like, for example, algae or carnivorous and so on. And by doing this formalization, we write that the variation of the weight of fish is equal to what goes in minus what goes out. So we may rewrite it in terms of what goes in is ingested food CT, minus what it is consumed. Fasting means this is what is consumed by a starving fish, so fasting catabolism. WT feeding is what it is consumed by a feeding animal, so an animal that is employing energy to feed himself. So this includes chasing food, as including food, consuming food, and digesting food. And then the rest is what it is non-digested, so what is this feces or excretion or losses due to non-metabolizable material. So if we write this equation in this term, we may, for example, write the ingested food as a function of the weight of the fish itself. So what we are introducing a dependency here on the weight of the fish itself. So you see that this differential equation is becoming more and more uh, different or displaced from first order, and we are losing linearity because we are including a dependency of ingested food on the weight of the animal itself, but on a power of the weight itself. So this is a nonlinearity. Here the assumption is that we include a parameter that is the feeding level, describing at which level the animal is feeding itself, and we are including the assumption that the food absorbing surface is somehow proportional to some power of the weight of the fish. This is not so strange. Biologists knows very well, but for example, the surface of the intestine, it is the absorbing food surface on an animal that performs digestion through digesting tract trait is somehow proportional to a dimension of the animal, but maybe, for example, the weight of the animal itself. The proportionality is not linear, so we may introduce a nonlinearity by saying that the food absorbing surface is proportional to a power or weight of a fish. And now we are left with the problem of estimating the energy of fasting, the energy consumed by a fasting fish. I recall you, a fasting fish or a fasting catabolism is a fish that is starving essentially, so a fish that is surviving but without consuming energy for feeding itself. In this case, we rewrite the fasting catabolism term in terms of the weight of a fish with another dependence, a non-linear dependence on the weight of fish. So the assumption is that K is a coefficient of fasting catabolism, so this is a parameter or coefficient of your model. And the second assumption is that some experiments on respiration demonstrate that fasting catabolism, so the energy employed by a starving animal, is somehow proportional to a power of the weight of the animal. Again, this is nothing surprising. Uh, this has to do with the allometric relationship we have seen here and there during our discussions. So we may find some kind of allometric relationships that links, for example, metabolism to an indicator of dimension of the organism, but maybe the weight. For the feeding catabolism, we have to include a model which we describe the fact that the ingested food is not all taken or processed through by the digestion processes. So we include a parameter beta, that is the fraction actually taken of the food consumed. So even in the process of consumption, the food consumed is not all processed or transformed into metabolizable material. Instead, a portion of this food is lost, and we indicate this by including a parameter beta. And then we include a further assumption, but in which we describe that the fact that the feeding, sorry, the fraction of the food intake, it may be used for one portion or a fraction of the food intake of the energy obtained by the food intake is employed itself to perform the process of digestion. So we have a further term, alpha parameter, but reduces further the quantity of ingested food by including the fact that some of this energy is employed for the digestion process itself. So this is called the catabolism of specific dynamic action. Please note that all these parameters, K, beta, and alpha, are all in the range 0, 1. This means that a zero value of the parameter means that we absolutely no transfer of energy, while a one value of this parameter means that the organism is performing perfectly, or what is taken is transformed into organic matter of this period. Of course, one is never possible and zero is never possible as well, so the reality is in between these intervals. Then we have to recall that some of food is lost during the digestion processes, so that some of the food is immediately converted into feces and excreted. We include this by simply saying that of the quota of food beta of ingested food, so that is the fraction actually taken of the food consumed, the reverse part 1 minus beta is the quota that is lost to the feces. This is why we write that the weight loss due to non-digestion is equal to 1 minus beta times the quantity of ingested food. We put all these together, and with some very easy algebraic calculation, we obtain this model, that is the Ursi metabolic model. The Ursi metabolic model says that the variation in times of the weight of a fish is equal to this parameter, beta, alpha, and so on, f, multiplied to two powers of the weight of the fish itself. So you see this is a non-linear first order, because we have a first order derivatives, non-linear because we have dependency of the power of a state variable w. And if we may assume that alpha, beta, f, and h are approximately constant, then we may rewrite this model by simply saying that the variation in time of the weight of the animal is equal to a large constant h times the weight of the animal elevated to power n minus losing decreasing quantity that depends on another parameter k and depends again on a different power of the weight of the animal itself. So this is also called Ursin metabolic model. When we try to analyze this curve and what you may expect to find, you find that there is exactly the logistic or sigmoidal shaped curve in which we have a dependence of the weight of the animal time that is described by a sigmoidal curve, in which we have the inflection point here in which we have the highest speed of growth, maximum growth rate, and then we have an asymptotic weight to which the fish tends when time goes to the infinity. This is the solution of this differential equation in the case in which the power, the exponent m is smaller than the exponent n. In this case, we have the fact that the limitation effect due to this negative term to a growth that decreases the growth quantity of material depends on the weight itself to a power n of the weight itself, and in this case, the fact that the power m is smaller than the power n means that the limiting effect is larger than the growth effect. On the contrary, if we consider the reverse situation in which m is larger than n, in this case we obtain an exponential growth for which uh, we have that the weight of the animal grows indefinitely with time. Of course, we have said several times that unlimited growth is an ecological nonsense. So this means that this model, this part of a model in which the limiting effect is smaller than the growth effect, is applicable only on the early stages of growth of organisms. Once the organism starts aging or grows, then the behavior of the model, of the UC model, tends to change into a sigmoidal behavior in which you have an asymptotic weight. So you do not have anymore an unlimited growth model. Instead, you have a limited growth model for which there is an asymptotic weight that represents the limit. Um, I recall you that this model is based on the assumption that metabolism is equal to anabolism plus catabolism. So we may write this in terms of a model as we have written here. So for example, if we assume beta equal to 1, so we only consider the growth term, we obtain this kind of curves, and you see that depending on different values of exponent of weight of a fish, we have different curves. So we have if we have a 1/4 exponent, we have a fasting growth. If we have a very almost zero exponent, we have um, almost zero means zero point 0.9, or sorry, almost one value of exponent. We have a kind of uh, behavior that tends to a constant. So the growth is less and less significant. Uh, Obvious, we have a special case of this model, of the Uchi model, that is the von Bertalanffy model. And this is important for historical reasons because this model was developed by von Bertalanffy at the beginning of the 20th century or the end of the 18th century, of the 19th century, sorry. In this case, von Bertalanffy recognized that there was a dependency on the state variable x, in particular, that is the weight of the animal, and this dependence may be made through power in the case, a power n in the case of growth part, and maybe dependency directly on the weight in the case of a growth limitation. Von Bertalanffy discovered that the exponent in this case for an optimal growth animal was 2/3, and we has declared a series of consideration linked to the topology, to the geometry of these organisms or animals in a three-dimensional space in which there is uh, a priority, in which there is a particular situation due to the verticality, in which we have gravitational forces. So the vertical coordinate has a peculiar behavior due to the fact that we are on a planet in which we have a strong gravitational force that is on the verticality. So the interesting part of a von Bertalanffy reasoning is that when 2/3 exponent that produces a Nursi model with a sigmoidal behavior in which we have a limited growth described by the presence of an asymptotic weight, and this was typical for growth exponent in the range 2/3 ones. So if the growth exponent of the von Bertalanffy model was in the range 2/3 ones, when we had this kind of sigmoidal behavior. So we immediately recognize that the 2/3 exponent may have a particular meaning. The assumption in this case is that the catabolism, I recall you, is proportional to a weight of a fish, and one of the assumption we employed in building this model is that the area of the absorbing surface for food is proportional uh, to uh, to one indicators of dimension of the animals, in particular the weight, body weight, and in particular this may be formalized by saying that the area of the intestine of an animal is proportional to the two-thirds of an exponential two-thirds of the body weight. So these two-thirds, um, as I told you, suggested what shall be present a general law for which all the living organisms on a three-dimensional world with a particular vertical, a particular one coordinate, one of the coordinate behavior that was affected by gravity. So some topological consideration suggesting that uh, the exponent should be the ratio between the two dimensions of the surface and the three dimension of the volume. So this is the meaning of the two-third exponent. This is quite interesting because we have tried to find the general laws to generalize this model. For example, there was a paper by Banavar and Rinaldo of 2002 in which they demonstrated some topological constraints on a 3D world with a privileged vertical direction due to gravitational forces presents. So these topological constraints uh, seems to be converted or may demonstrate that the exponent shall be in the range two-thirds, three-quarters. And these two exponents are often very often found when you try to infer general laws on biological processes. For example, laws that applies to several scales as the allometric relationship we have seen before. In a case of a three-quarter exponent, Banavar demonstrates, Banavar and Coulter demonstrate that we are in an optimal value situation in which there is a supply what is exactly what is demanded in terms of for growth. So supply is equal to demand, this is the upper limit reported. In the case of a two-third exponent, the network we say is oversupplied, meaning that supply is independent of the dimension of the animal itself, of the organism itself. This means that if we want to describe somehow limited growth, the exponent should be in the range two-thirds, three-quarter, and the more the exponent is close to a three-quarter value, the more the growth is limited. Um, we finish this lecture of today by giving a review of some of the metabolic of some of the models of population growth. We have said we started by linear growth. Linear growth means that we increase or change in times of the weight of the animal is equal to constant. Malthusian is the exponential growth, so we make a dependence of on the weight of the organism itself. Of course, this is the first order kinetic in which we have a dependence on the state variables x. You know very well that the solution of this differential equation is an exponential growth, but then we have seen that uh, exponential unlimited growth is ecological nonsense, so we have to include some limiting effects. And we may include this by, for example, multiplying, introducing a nonlinear dependence on the weight of a fish in the decreasing or limiting part of our differential equation. So we may write the equation of the logistic growth in general terms, and we find that the general solution is the one written here is the analytical solution of this differential first order differential non-linear equation. The properties included or implemented in this description is that the growth is limited by a carrying capacity factor K, and that the maximum growth rate is reached at the inflection point, so in which we use the semi-saturation constant value K up. We have already seen the semi-saturation concept when we have introduced the Michaelis-Menten curve model, or the Michaelis-Menten model, in which we said that the Michaelis-Menten model depended on a parameter that is called the semi-saturation constant. So the point at which we are exactly half of the way to a saturation value of the growth. So this is not surprising because we are always employing the same approach: energy conservation, continuity equation, and forcing first order and not too far from the linearity conditions, we obtain this kind of descriptions. We know that the solution of this is a sigmoidal curve fascias. So the general equation of a sigmoidal curve is this one, in which we have a function phi, but depends that generic function of the growth rate r that changes, of course, in times. And so this tells us the different shapes of the different aspects of a sigmoidal growth model. We historically we may find some uh, other application of growth model, for example, the Gompertz model, in which the assumption is slightly different. We start from again from a first order dynamic linear differential equation, but we include the nonlinearity by saying that the growth rate R depends on the number of the population itself. This is as to say that the assumption that mortality grows exponentially with the number of the population. This is something that may often happen ecologically speaking, if we have an increasing population and mortality typically tends to grow exponentially. And you include this by rewriting your differential equation. Instead of a single equation, you write a system of differential equation, first order differential equation, in which you have an equation for the dimension of the organism and an equation, a differential equation describing the growth rate of the organism itself. By this consideration, we may also include some specific aspect. For example, we may include the fact that not all animals are ready to replicate themselves when they grow. Of course, when we think at bacteria tends to split. So every time a bacteria splits into two offsprings, then the offsprings are immediately ready to split again and to grow. To the population may grow. This is not the case, especially if we consider more higher trophic level populations or more higher trophic levels organisms, in which, for example, we may include the fact that the reproductive maturity is reached after a specific amount of time, in particular TM. If we include this, we obtain the so-called logistic with delay, in which we have a growth that is typically sigmoidal or logistic, but you may have, when you are approaching the asymptote, you may have a crossing of the asymptotic value. So you may have a lower population, but suddenly starts to die exponentially. So you go beneath the carrying capacity or beneath the asymptotic weight, and so there is an oscillating behavior that is driven by the lowest trophic levels. Okay, this more or less concludes the growth model I wanted to present. So today we see we saw that we may have an approach that is very uh, holistic, in which we renounce giving the details to the processes, like is the case to nutrient load generated by large river systems, large catchment, for which we were able to build a model that allowed us to make some forecasts and to management scenarios. So this is the utility of applying also an holistic approach model without having too much details. But on the other hand, we may include a lot of details on the physiology or biology of the organisms that are growing. So we may have a different approach model in which we include um, all a lot of information concerning the physiology of the organism, and we may, for example, employ a metabolic balance, uh, eh, obtaining a URC model, but is a metabolic growth model in which essentially we describe a process of growth in terms again of energy flows. All this is based on the principle that energy is conserved. So the second principle of thermodynamics.